We have to stay up till like
tonight.
11.
No. So that means that when this is over, you need.
So let's make it quick.
Oh.
All right. Let's do everything quick and thoroughly, of course, but quick. Polar and electronegativity. Those are two things you guys want me to talk about. So let's do it. If something is polar, means that it's pulling electrons to one side or another side of a molecule, right? So you can tell if something's pulling electrons to one side of the molecule if you've got an element on one side of the molecule that's more electronegative than the other part of the molecule. Electronegative means an atom's ability to attract electrons. So if it's more attractive for electrons, it's going to be pulling those electrons towards it. So for instance, if you have, I give this as an example every single time, if you have something like this, where you have fluorine over here, you can see clearly, without even knowing what the three-dimensional shape is, that each one of these hydrogens is being pulled into the middle towards carbon. Their electrons, that is, get pulled in the middle towards carbon, and then carbon's electrons get pulled towards fluorine. So you can tell just by looking at this molecule that if fluorine's on one side over here, it's going to be polar. And that's all you really need to do, is you just need to recognize that it's going to be polar. Okay? So this is definitely polar. It's a polar molecule.
You can just see it by tip the scale.
You can see that fluorine is more electronegative, and you can tell how electronegative it is from that chart that I gave you, that you'll get on the test. I get lots of hands. Noah first.
If you don't like the chart, then how do you know how electronegative like
Yeah, so you can remember the trends if you don't have the chart. If you don't like the chart, just remember the trends. The higher up on the periodic table, the more electronegative, and the farther to the right, the more electronegative. Let me do it the other way around. So if you're looking at it this way, the higher up, on the periodic table, the higher up, and the farther over to the right. So this fluorine would be the most electronegative atom on the whole periodic table. Yep.
I have two questions. First one, that's gonna mean it's a hydrogen bond, right?
That's not a hydrogen bond, actually.
How come? Because I thought it had to have a hydrogen.
Oh, actually, yes. No, you're wrong. Because that fluorine has to be bonded directly to a hydrogen. Yeah.
Okay. And then my second question is this similar to like the problem if we had N2H2?
N2H2, that molecule N2H2?
Yeah, if we
Yes.
did N2H2, that would be polar, right?
That would be polar, yes.
Okay.
And do you want to walk through that one?
Yeah, could be.
Yes, and you have a question.
Do we need to recognize which side is partially negative and partially positive?
Only for really simple molecules that we always do, like water, or like if you have something like this. You can tell which side is polar.
And to find it using the chart, and like if you don't know use the trends, do you just subtract the numbers from each other
To find the difference in electronegativity?
Yeah.
So if
Does
there's
that
any
tell
difference.
if there's any difference at all,
Yeah.
it means polar? Oh,
Yeah.
okay.
So that really means that you've got two different atoms. One side's going to be pulling stronger than
But
the other
if they're the
side.
same, then it's not.
Right.
Wait, so what's the rule with the numbers?
Yeah.
If you want to use the numbers on the chart?
There is no rule. The higher the number, the more electronegative that atom is.
But like, how would you use that with this fluorine card?
So for instance, fluorine I think is, what is it, 3? Or is it 4? I can't remember. On the chart. Whatever that number is, then you know that it's higher than the carbon.
The
So that's something you
electronegativity.
really know.
So as long as the fluorine's higher than the carbon,
That means it's pulling towards,
then it's polar on the fluorine side.
yes. Good. Yes.
Because it's partially positive.
It's partially positive or negative because it's a covalent molecule. The whole thing is covalently bound. That means they're sharing electrons. So you can't get a full positive or full negative on this, okay, on one side. It's always going to be partial positive or partial negative. Now you can calculate how positive and how negative it is, but we don't go into that level of detail. We just want to tell you guys that it's partially positive and partially negative. It's like that for all molecules, okay?
Including ionic bonds.
Ionic bonds are not. That's different because they're not a non-molecule. They're lattices. They're big
Okay.
complex of lattices than on a molecule. Yeah.
So like in this case, is fluorine the one that's partially negative because it's pulling more electrons?
Yes. Exactly. Let's do an example, like Sophie said, with N2H2. 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 And you can try to figure this out on your own really quickly if you'd like to. But here's what it looks like. Blue. We've got N. And how many dots are around N?
2
Five.
and 3.
1, 2, 3, 4, 5. Right? Each of these are single dots. So that means that they're available to do bonding. And they're going to bond. And I'm just going to put the H's over here. Each H has 1 dot. Now you just connect the single dots to get the whole Lewis dot structure. Right? Alright. Oops, that's connected. That's 1 dot. Now connect these dots. Connect these dots. So, we've got this. You can choose either one of these nitrogens. And you can tell me what the shape is around those nitrogens. You can say, okay.
It's gonna be polar, right?
Is it trigonal
Yeah.
planar? Right, I'm just guessing. I need to memorize this thing.
That's linear.
Is it linear or is it trigonal
No,
plane?
wait.
No,
Why
wait.
is it?
Or is it something else?
It is bent.
Wait, why?
That's so
Why is
weird.
it?
I'll draw it as if it's bent.
But can't you draw it the other way too?
You could draw it the other way for a Lewis dot structure, that's fine. But this tells you a little bit more about what the shape of this molecule looks like, right? So here you can see, alright, now that it's bent, clearly it's bent, and 120 degrees.
I'll see it.
So
Wait, why isn't that linear?
it's not linear because of this right here. That pushes
Oh,
down the bond.
If you include that, it's 120 from the H to
Oh,
the.
like
yeah,
that causes them to
Yeah,
like
yeah, yeah.
It causes
like,
them to be squished down there.
Yeah.
Yes, exactly.
Wait, since when is that?
Because negative is opposed.
So,
look what you did. You knocked over the video camera.
let's just put it back up.
Hey, put it back
Wait,
on.
oh, I thought you marked it off the.
Hey Dean, can you possibly move over? I can't really see it.
I understand.
No, I mean like when you're by yourself.
Oh.
No, not in my direction.
Alright, so let's see here. This is pulling each one of these bonds. You can see, well,
Thanks, Dean.
that nitrogen to hydrogen bond right there, it's definitely polar. It's going towards nitrogen. The electrons are being pulled towards the nitrogen. Over here, there's no winner. Nitrogen's fighting the other nitrogen, so they're both pulling evenly. It's going They can't pull either way, so there's no dipole on that kind of bond right there in between the two nitrogens. So it's a stalemate. It's like a tug of war. Nobody's winning. Here's the reflection off my head. Isn't that funny?
He's been off by.
Okay. Funny. Now,
So that means it's polar.
yes. So now since there's nobody winning in this battle, but here it's pulling the electrons in this direction, that means that it's going to be polar over here. This is partially negative over here, and this is partially positive right over
I
there.
think the best way to know this is by actually doing it to detail, adding them up.
If
If it's a complex
yeah.
What about the
molecule,
nitrogen on
like
the
some of them are.
Wait, is this
So,
one polar?
so over here you can see that this now is a partially negative side, this is partially positive, so since it's like this, it's going to be polar. But we have to think another step ahead now. It's not just polar, but it's got this special bond. We got an N to H bond, which would make it what kind of intermolecular force? Yeah! Hydrogen bond's right, so this is definitely a hydrogen bond. H bond.
And what exactly makes that different from the regular
Polar.
polar bond?
It's just as a special case we've got N to H.
But does it act differently?
It acts stronger than most of the
So it's the
dipoles.
strongest polar bond.
Yes.
Or strongest bond.
Yes. So if we want to rank these, this is a great question right here.
Right? By the way.
So if we want to rank these right now, from the strongest kind of intermolecular force, from the strongest type of intermolecular force to the weakest type of intermolecular force, the strongest would be hydrogen bonds, the second strongest would be dipole-dipole,
Yeah.
and the weakest would be
Van der Waals.
Van der Waals, that's right. Van der Waals is with the non-polar,
They
right?
haven't.
I have a question about like the disco move.
The disco move.
Yeah, does that work with the electronegativity as well? High, low, high, low.
Yeah, that could work.
What's the disco move?
Boom! It works for Harris.
I don't get it.
Disco.
Look. Low, high, low,
What
right?
does that
Yeah.
refer to?
There we go.
Sorry,
Hey,
we just need some filter feedback.
okay.
And we're gonna be
All
given that
right.
sheet.
What else? Is that all the questions you have right there? I think that's a good cover.
Could you?
Oh,
That's pretty
okay. Yeah, what's up?
Like, you know, like on the right side, the hydrogen was like going towards the nitrogen, but then like
Yeah.
how about like the other side?
The other side's doing the exact
Doing
same
the
thing.
right? But
Yeah.
then, like, this is gonna be like non-polar. So, like, can you give us an example of a non-polar?
Oh, yeah, sure.
So yeah, so is this polar?
Don't pay attention.
What's this?
This is the easiest kind of non-polar.
Was that one polar? The one we just did?
Yes. I'm going to do this. This is an example of a non-polar molecule. This is, I'm being very nasty to you guys right now. Okay? This right here, you can draw this out.
Oh yeah.
Okay, you can draw this out, and it'll look like this. I'm skipping the dot step, just so we can get this done faster. Let me get to the main point faster. So here is CH3, CH2, CH3.
Yes.
Now, in each one of these carbons around here, the shape around that carbon is going to be tetrahedral, right?
Yes.
Shape's going to be tetrahedral. And each one of these carbons is going to be pulled towards, I'm talking about their electrons, of course. Their electrons in the bonds are being pulled towards the carbons. So I'm just writing out every single one of these dipoles. Right?
Wouldn't this be polar? Non-polar.
Now, Lewis dot it's difficult to see. In this case, it actually shows pretty well how these vectors cancel each other out. But in 3 dimensions, it gets more complicated than this. You can tell from the Lewis dot structure, though, just from here, that these all cancel each other out. You've got one going this way, and one going that way. One going this way, one going that way. And they each cancel each other out. Notice there's no dipole in between each of the carbons, because there's no winner there. There's no one carbon that's pulling more. They're just equally tugging on each other.
Isn't that for a negative, like a non-polar?
So this whole molecule is really equally distributing its electrons. It's a very equal distribution of where these electrons are in the molecule. So there is no one lopsided end to the molecule that has more electrons than another end. It's all equally distributed. So it's called nonpolar.
That's how you classify it?
It's nonpolar, yeah.
Even if we wrote that, would we still have to write whether or not it's like...
But
what
it still
best
is
for
polar
someone?
Well, it's nonpolar. Let's say, and then more to Naomi's question. If I bold one of these C's, like this one in the middle here,
Yeah.
you can tell me which shape, which molecular geometry is around that C right there. What is it? Yeah, tetrahedral. It's tetrahedral. And what's the angles for the bonds? What's the bond angles?
Oh
Taji?
wait, 109.5?
109.5, great. What else? What kind of intermolecular forces would be between this molecule and an identical molecule? Yes?
Just because you can't really tell us the shape of the entire thing, right?
Well, you could tell the shape. You could say that's tetrahedral, that's tetrahedral, that's tetrahedral.
Yeah, but you can't ask us like what's the shape of the entire.
The whole molecule, no, that doesn't make any sense because you have to say
You have to
three
choose
tetrahedrals
one
stacked on top of each other.
One part of
So
it.
then it would be Van der Waals.
Yes, the intermolecular force is van der Waals.
But when you're saying that, you're not just looking at that one carbon that we bolded, right?
Right.
Looking
You're
at
talking about the intermolecular force, so the force felt between this and another molecule. Okay? Questions about this?
Yeah, sorry. I know it's confusing, but the arrows are called
yes, if the force in between here is not dipole-dipole, you can still call these dipoles, right? It's that there's no polar and polar molecule right next to each other. It's still, there's individual, each one of these bonds, is this being partially positive and this being partially negative.
Dipole-dipole is usually when you have like two large bonds and they're like the same kind and they get to each other?
Yeah.
Or does it not have
Two
to be
large
the
polar
same?
molecules, you mean, right?
Yeah, that's
Yeah.
what I meant. But do they have to be the same molecules?
I'm always going to ask the same molecule. They don't have to be, but in my questions, they're always
Wait,
the
what
same
do you mean
molecule.
by same molecule, like H attached to H?
I'm saying, if this was attached to another one, just like this Taji right here,
Yeah,
if this was attached to another one just like it,
yeah.
that's what I mean, the same molecule.
Oh, okay. But that's not dipole-dipole.
No, this is what?
That's van der Waals.
Yes, it's a van der
Oh,
Waals.
and I have one more question.
Okay.
For the connection of the same element, why would it be classified as non-polar? Because it's still tugging, but...
Yeah, but overall, there's no imbalance of those electrons.
Oh, okay.
There's no imbalance at all. So they're all equally distributed in this molecule. Yeah?
For dipole-dipole bonds and attachment go between two polar molecules, can't you consider hydrogen and carbon polar molecules?
You can consider carbon and hydrogen right here as a polar bond, right? But the whole molecule itself is not out of balance for its electrons. So that means the carbon's going to be slightly more negative than each one of these hydrogens. That's right. But overall, the electrons aren't shifted to one side of the molecule. It's all even. It's all symmetrical around that molecule.
So does that mean that each bond there is just a dipole?
Yeah, you consider each one of these a little dipole, right? But when you add all the vectors up, they eventually cancel each other out, and you get this even distribution of electrons. Sophie?
Yeah, what if you're given, I don't know if we've done this or I'm just like being stupid right now, but what if you have like a valence electron as one of your like, can you ever, is that ever going to happen where you have a valence?
An extra electron?
No, I mean like like
Valent. You mean
transition.
Transition metals, they're metals, so they're not going to enter into covalent bonds.
Okay.
These are all covalent bonds when we're talking about IMFs. You guys also know? Okay. Brandon. What are you doing?
I can go to baseball practice. I only got 30 minutes. What? You wanna come back after? No? Stay.
Okay. You play baseball soon. Okay. It's preseason. All right. Now, this is a non-polar bond, right? Now, we've done polar bonds, we've done dipole-dipole. You got a question yet?
Give us a clear definition of what exactly dipole-dipole is. Like, what happens when there's a dipole?
What happens? You've got two polar molecules and they attract to each other. That attraction is a dipole-dipole force.
Each pole, like from the polar molecule, attracts to the opposite pole of the other one.
Exactly, perfect. Yeah, perfect. Good. Yeah, Taji.
Does this only apply to covalent bonds, or does it?
Yes. Just covalent.
So IMFs and everything is only covalent. Why is that? Okay, no, I don't.
Because molecules, by the definition, molecules are just covalent bonds. Okay? Ions make lattices.
So you don't ever have to worry about transition metals in there and stuff like that.
No. No. Question?
No, just question. Yeah,
Okay.
like, what if, you know, like the one we did with like CHF?
Yep.
That one was polar, and the one we did N2H2 was polar, so like, if they bond, that's a dipole-dipole, because they're two polar.
If a CH3F and a CH3F are next to each other,
No, if like a CH3F and an N2H2 are next to each other.
yeah, then they would bond. But you couldn't call, yes, they would, I wouldn't say bond, I would say they're attracted to each other. Be very polar attraction. Like polar bears and love.
Can we go over?
Be Vesper.
Alright, the last one, then we're going to move on.
What's the difference between the van der Waals and the dipole dipoles?
The van der Waals is just with nonpolar molecules. Van der Waals forces are the attraction you feel. Look at this right here. This is an example of van der Waals forces. If you zoom up really closely on these atoms, here's an atom, there's an atom. If you zoom up really closely, you can see that that H atom right here and that H atom right there, that's their nuclei right there. And they each have their electrons too. Right? They have their electrons. Now, a van der Waals force is when you have one of the electrons attracted to the opposite nucleus. Okay? It gets so close. It gets so close to the other nucleus that it actually starts getting attracted to the other nucleus.
But they
So that weak attraction right there, that is what we call the van der Waals force.
How can you tell when there's a van der Waals?
If the only way you can tell is if there's two nonpolar molecules next to each other, is they bump up next to each other, they're going to feel some of the attraction. They're just so close. It's the proximity. They just get so next to each other that they start to attract the other electrons. Okay, so that little weak attraction is what we call the van der Waals force. Okay? Okay, yep.
Me?
Yes.
How would you connect that? Would it matter what H you put to H? Like if you said should
No. I could have chosen this one, attracted to that one. And then this would get out of the way.
Oh, so we don't show this like we did an example in class with water, like
Yeah.
a specific way it should.
to be drawn.
The
so like
hydrogen
to the
bond,
side.
I think, or dipole, I don't know, I forget.
But that was one of the hydrogen bonds.
Hydrogen bond.
Yes, hydrogen bonding. No, it doesn't matter this way.
So we just have to show that.
Yes.
Okay.
Yes. And yes, last one. The last. Yes. It's okay.
They switch back and forth though. It's not like they just stick to one electron to nucleus, right?
They oscillate. Okay. That's the polar electronegativity.
Oh my goodness.
That was it. Okay, you guys are pretty well prepared.
Okay.
Now, what do we want to talk about? We want to
Vesper.
talk about IMFs.
Can I talk?
Vesper we talked about already within this. So that,
We talked about Vesper and IMF.
okay, see you. All right,
Can we?
we got three
We did
things.
IMF.
Let's do IMFs real quick.
We did it.
IMFs we talked about a lot in period 1 class. You guys talked a lot about IMFs. Period 4,
Did we just do it?
not so much.
We just
You guys need to learn about this a little bit more. So IMFs, the strongest types of IMFs are, as we said before, hydrogen bonds. Right? The more hydrogen bonds you have in a molecule, the stronger the IMF. Right? Right?
Yeah.
That makes sense? So if I ask you a question, which one of these molecules is stronger? This one. This one. Or this one. And she's back. Oh, it's Christina.
The left.
Buenos dias.
Which one
The left.
has a stronger IMF?
The left.
Stop. Give me a moment.
Is it going to be this one, maybe? Or is it going to be
Wait, I don't know.
The right.
A or B? Who says A?
Hey,
Who says B?
I don't know.
You don't know.
How do you figure it?
The stronger the IMF.
We should close that door because that song is really loud.
But here there's so many different elements to find the difference in electron negativity. Like how do you can you focus on one particular part of this? Because I know you said
the B.
stronger IMFs are when one of them has a higher difference in electron negativity.
Yes, or just more hydrogen bonds or more polar sides.
Okay.
So in this case we have lots of areas for hydrogen bonding. In this one we have 2. In this one we have 1. So this one can form one hydrogen bond with another identical molecule like itself.
So
This one can form 2.
that one's stronger.
So this one would have a stronger intermolecular force, which would give it a whole bunch of other properties, like it would be more viscous, meaning that it doesn't flow as easily. It's more sticky.
What about its boiling point?
it would have a low. What kind of boiling point? Would you think it would have a lower boiling point, or a higher boiling point than
For the
this?
stronger ones?
Higher.
It would have a higher boiling point.
Yeah. Because it's harder to break apart.
It's harder to break apart.
Oh, wait, so wait, you said here, you can look at the, you can see that there's more hydrogen bonds or more polar sides.
Well, yes, or a more polar side, I should say.
So wait, like, how did you, I'm sorry, like, I'm having something walking with you, but how did you figure out that that had a stronger IMF? Can you show that?
Because there's two OH bonds over here, and there's one OH bond over there.
But what if they don't even have, like, OH in common? What if they have, like,
That's a different example, though. But for this one right here,
yeah.
they have OH. The only difference is this has two OHs, that has one OH.
Okay.
So here you're comparing this to that. It's pretty easy to see. This one has two of the OHs. This one only has one. So this one's going to have a stronger intermolecular force, which is also going to make it have a higher boiling point, and also have a higher melting point, I guess you could say too.
Can we do another example?
And a higher, what else? Just stickier viscosity. It evaporates less quickly. What else do we think of? I don't know. Yeah, Andrew.
If you had C4 and CF4, which would be stronger? Because I know fluorine is the most electronegative, but hydrogen bonds are really powerful.
CH4 or CF4, which one would be more powerful bond? That's a good question.
It's so tricky, man.
That's a really good question.
Wait, what did you just say?
So Andrew asked if you have CF4 or CH4, which one would have a stronger intermolecular force, right?
Yeah.
Go ahead.
Here's CH4, here's CF4.
And also,
Now, Andrew, this question really goes beyond anything I'd ask. Okay, this goes beyond anything I'd ask. Because to answer this question, you have to think, okay, so how is this going to work? How are these things going to be pulling their electrons? They're both going to be nonpolar, right? I hope you all see that. It's going to be
The pull
nonpolar.
between the carbon and the hydrogen, the carbon and the fluorine.
Don't you
are
look
different.
at the one that has a higher electronegativity?
Well, think about this. Which one of these is going to have more electrons available to pull and to push? I would say I have to do some thinking about this. Because it's not clear to me, just looking at this, which one's going to have the stronger one.
Yes.
That one is
This has more, each one of these electrons is pulling really hard onto the outside. Right? But more electrons doesn't necessarily mean, I would actually say that this one has a stronger IMF. Now this is beyond anything we have to know for the test, but I'd say this one has a stronger IMF because here you've got all of those electrons surrounding the nucleus, which would block other neighboring electrons from being attracted to the nucleus. So in a sense, it'd be like shielding it from the nucleus. Here you only have one electron, so it'd be easier for other passing by atoms to be attracted to it.
oh, because it's got a smaller it's got a smaller radius.
Yeah, this one has a smaller radius. This one has a larger radius, actually. Because this one has everything shrunken in. And all the electrons are right around it, really close to the nucleus. So the nucleus doesn't really have all that much of a chance to be seen by neighboring electrons. You know what I mean? Over here, it has a little bit more of a chance to be available to other neighboring electrons. So I'd say this one would have a stronger IMF. But this is, again, beyond anything I'd ask.
Are you asking that on the test?
No! No. Don't get worried.
I'm still kind of confused.
Okay, alright, Sophie, hold on a second. Lawrence has had his hand up for a while. What's up?
So, remember how I asked you earlier about like the numbers on the chart?
Yes.
How could you use that here? Because I feel like that's a simple way of figuring things out.
You subtract.
The numbers don't really matter here. The numbers, all they mean is that it's electronegative.
So then what's the most basic way to figure out which one's stronger?
There's no basic way for this. Like I
So
said,
it's you would never put that on a test?
no, there's no easy way to figure this out. You have to think about back towards when we're talking about effective nuclear charge and all that good stuff way before to even come close to a reasonable answer to this.
So what would you put on a test as like a what's stronger question or something like that?
Like what I did just before this.
Yeah, but how would you?
Yeah, but we didn't understand how how you figured that out.
Yeah, like what's the direct way of figuring it out?
Wait, can we not focus on this because it's not even gonna be on the test?
No, that's gonna be
No.
the test.
What-
No, just as that.
What I'm asking
So that-
now-
He's asking
What?
something else. He's not asking like
You're getting a little-
People are
Well,
crazy.
right,
You're getting kind of crazy.
not necessarily an example.
You're getting kind of crazy. All right, we're moving on from what Andrew's question. That was a good question, but it's not going to be on there. Let's talk about this. These two molecules look very similar, don't they?
Yes.
Here's more to the point that you were asking before, Sophie. Your question was, what if they? How do you know if something's more polar or a stronger intermolecular force?
Well, here you would just
Here.
look at the electron negativities between C and F,
Here you
and
go.
C and Cl, and then see which one had the bigger one, and you can see that that has
What do you
stronger.
mean?
But not all of your examples are going to have so similar, except for like
Why would I not do that? I mean, I don't understand why I wouldn't do that. I would make it very simple, so only one thing is different.
oh
so
really?
so there'd be no other argument against it.
So how would you
I thought you were
place the question? What would the question be?
The question would be, which one has a stronger surface tension?
What?
Exactly.
Put it in English now.
Surface tension. Which molecule would have a stronger surface tension?
I don't know.
Wait, that one's stronger.
Can I-
So let's break it down.
Can I say it?
Yeah.
Okay, since I think fluorine it has a stronger electron activity than
Yes.
chlorine.
Yes.
That means that one is stronger, has a stronger IMF.
Stronger IMF, which would also give you a stronger surface tension, because surface tension is directly related to intermolecular.
Wait,
Did we
but
talk about
I don't
superstar
understand how you figure that out.
Okay, look.
It's like
Do you see the C,
the
Cl, and the C to the F?
Yeah.
You see the only difference is that it changes from C to
I
F,
don't think we talked about that,
right?
We did.
So you're gonna go to this little chart.
Super.
Surface tension.
Oh, super tension.
Not super expansion.
I was like, what? Also, higher IMF is also higher
Surface tension. Yes, surface tension.
Wait, please hold for naming. Oh, wait, no. And wait, formulas.
Yes.
The stronger one would be chlorine.
A stronger one would be fluorine, yes.
And that's why it's a surface tension
Because
because half surface, it's tighter, so you can fit more.
at the surface of everything, this is a good point to add. At the surface of
Oh,
anything,
because
at the surface of anything,
But like, let's say another one.
the thing that is keeping any kind of molecule, I'm just going to say these are molecules right here. They're just generic molecules. They're little balls. The thing that is keeping them from flying out and becoming gas, the only thing that's keeping them from flying out and becoming gas, are the intermolecular forces.
And so if it's stronger, it's more,
Yes.
higher
So
surface tension.
the tension here at the surface, there's a stronger tension at the surface if you've got a stronger intermolecular force. Right?
Yeah.
Makes perfect sense. So that would also make sense for boiling point as well. So if it takes more energy to boil this off, that would mean it have a higher intermolecular force. So which one would have the higher boiling point? This or this?
Fluorine.
The fluorine.
And
Higher
it also
boiling
has
point.
a stronger surface tension.
Yes, we just.
Yes,
Yeah, okay.
exactly.
And this is
Okay. All right. I think we kind of got that, sort of. After some initial confusion, we got that.
Would you
Okay.
say higher or stronger?
Stronger,
Yeah.
higher, same thing. Naming.
Okay, please.
Naming.
I'm so
Oh,
bad
plus, right?
at transition
Yes.
metal.
The naming was
I hate it.
Naming's a rest.
the quest.
Yes.
Oh, I thought it was
So you
Okay,
got that
wait.
good?
So,
You can go if you want to.
senor,
I understood everything.
I'm glad you did.
We always did.
Now think about applying it.
senor.
See?
Alright, I'm Italian.
I have to.
Okay, so covalent bonds are easy. It's just like you look at like the numbers. It has like the tetra, like that kind of thing, right? For covalent bonds.
Yes.
Like if it's like P4S5, that's tetraphosphoric pentosulfide.
Yes.
Those are easy. And then, but then what about like? Sorry, give me a second.
It's okay.
So like sodium, like NaBr, you just write sodium bromide.
Yes.
Okay, what about like transition metals.
Okay, transition metals?
Yeah.
What about them?
Can you maybe give me some examples with
Sure.
the name?
Let's do formula to name.
Okay, and yeah.
Okay, formula to name. We just want to talk about transition metals, and we want to talk about anything else. Just transition metals? Just transition metals. Oh, let's also do polyatomic ions
So yeah.
with the transition metals or just a regular ionic bond.
Okay. Wait, polyatomic them together?
Oh my god, we can do it.
Yeah, he was like.
We can totally do it.
About it.
Okay, let's do it. This is so fun.
Hey.
So you got this, right?
Oh.
Are you confident? Yeah?
I feel good.
Good, great. Now, let's do some transition metals. Transition metals. Let's try AU, which is
Oh, I got one.
gold.
Wait, I need to hear.
No, you gotta give
Let's
me.
try this one. Gold, and then let's do gold.
Do you want mine?
Gold 3, P2.
Okay.
Oh my goodness. Don't say anything. Taji wants to solve it.
No, I just hear people like,
Don't
I'm solving
say
it, people,
anything.
like,
I know, it gets frustrating.
Yeah. Okay.
They want to review.
He was just talking smack.
Thanks,
about you.
Brad. You're
Don't
just
believe
saying
anything
some
that
really
guy
weird
says.
things. Just like jokes.
Like stuff about our advisor
You
group.
got it on tape. You can go to the tape too. No jokes. They're burning up.
Oh wait, now what I just said to be on tape.
Yep. Way to go, Lawrence.
Hi, camera.
Mr. Greg makes an appearance in every one of my review
I
videos.
honestly don't know what I'm doing.
he didn't even last time?
I really don't. Remember, I'm so bad at this.
Come
Like,
on.
can I transition
Me.
something?
No, no, no.
I
Lawrence, please. When you start explaining it, that nobody can hear anything else because I can hear your voice, and I even get distracted by your voice. It's not.
So
I thought he was
bad.
gonna
Because
say
you're
something
so
like
brilliant.
No, he's gonna be like, no one gets it. Like, that's where I know this is going.
I didn't go there, but that sometimes people do get a little bit more confused when you tell them things. Andrew,
I have two questions.
2 questions.
On the periodic table, at which point on the sections, which point do the metals turn into non-metals?
Which point? The staircase. See the stair step? See the red?
Yeah.
With boron, silicon, arsenic, tellurium, acetine. That's the step. That's the staircase that I talk about all the time. So there, on the staircase, either right above or right below, there's some that we call semi-metals. But you should think of anything to the right of the staircase is going to be a non-metal. Anything below the staircase is going to be a metal.
Isn't it like boron, silicon, phosphorus, arsenic, like those are semi-metals, I think.
Yeah.
Semi-metals are counted
They're
metals
like-
though, right?
So we are
As non-
gonna count them when we're naming them as.
Yeah.
I don't ever ask any questions about it like that. Silicon I might do. Silicon you consider a non-metal. You can consider a metalloid. So when we talk about metals and non-metals for covalent bonds and ionic bonds and how to name them, if it's to the right of the staircase, name it like it's a covalent bond. Okay.
Oh, really?
If it's to the left, you
Yeah.
got a metal, so that's going to
Just
be.
use them on the right and
So we'll,
It's easier way to do
So
it.
starting at
Will
aluminum,
D
metals, and that's ionic.
will D be then I metal?
With what?
GE.
With what?
Germanium.
Oh, germanium. GE.
It's a non-metal.
What's wrong with that?
Nothing is wrong with that.
Okay.
I'm
That's
just immature.
that's a metal
We consider that to be a metal.
because it's a metal. Tellurium.
Just for consistency's sake, we're going to say that that's a non-metal.
Okay.
Okay?
But that's the right.
So it's a little
Oh yeah.
staircase.
Would you
Just for consistency's sake.
phosphide?
Excuse me?
Would you just say gold phosphide?
And gold too. Phosphide.
What, how do we name this?
Wrong.
Let's go back.
Stop, guys!
Gold blank phosphide. How do you name it?
Oh, right, for transition you need those little in-between numbers.
Yes, the little in-betweenies.
Yeah.
The in-betweenies, what is the in-betweenie?
2.
2. Why is a great word.
Wait, but it's really
Why?
hard because like you have to for the transition metals, you have to like count to find out the valence electrons. Like you have to like,
I'm sorry. So do you understand how to get this, or should we walk through it?
wait, can we just walk through this?
Yes, let's do it quick.
Stop, Christina, if you have a problem.
It's a little bit too loud. I notice it's a little bit hard to hear what you guys are saying, so it's going to be really hard for anybody at home watching this to hear what I'm saying. So, right here we have AU, that's gold, and in this little formula it says there's 3 AUs, so I'm just going to draw 3. There's 2 phosphorus, so I'm going to put 2 phosphorus right here. Got it? Now, I don't know how many each one of these AUs are giving up. No jokes. Then, each phosphorus has 5 valence electrons, right, Lawrence? Right.
I know this.
I'm glad you do. And then we have 3 places for those electrons to fill up in phosphorus. Okay?
Oh wait.
So overall, we have a grand total of 6 electrons that need to be put somewhere, need to be placed somewhere, right? So since we have 6 spots to fill, we need to think how those 6 electrons are going to be distributed evenly among all these golds. These golds are going to be giving up 6 electrons overall, right? Because we've got these 6 holes to fill. So since they need to fill up all 6, how are these going to evenly distribute 6 electrons? And the only way to do that is to say each one of these golds gives up 2.
Wait, why would you say that?
6 divided by 3.
Look, now they'll fill in all the holes.
Give up 2 anyways.
Fill in
Transition
the
metals
holes.
give up 2. No. Wait, that's not true. No, it's 2 that came.
Now you see that it's for 3 golds and 2 phosphoruses. You need to have each gold give up 2. Okay? Okay. Yes, then yes.
Okay.
You have another example you want to go through.
Yes.
Okay.
It's called W.
Wait.
Okay, I'll put this up here, and then I'll have Taji ask and then Naomi. So W2, O2.
Wait, did you say there was the trick where it's like the AU3, like the 3 means like the P, like there's 3 for P, and then like the 2 means that AU is giving us 2.
Don't worry about the reverse crisscross applesauce. If this is confusing to you, just use dots and holes.
Does that work?
Yeah, that's how I
Like,
What's so funny? You guys are having a nice little laugh.
I just love chemistry.
I see it.
I used to do
Love it.
I
Want some more of it. I know you do.
I'm serious.
Next year, you guys are going to say, oh, remember back in the good old days, Mr. Sand? Back in the good old days when Lawrence was up to no good. He's doing something.
No, that's what he said. See, look. Right?
He's
Do
smiling.
I actually doodle about? Oh, she wrote I heart cam.
Look, I think
There it is. Well, there's a psych involved. That's not good. So do you have any questions?
Yes. What's the range of the amount of electrons that a transition element
Can you give up? I didn't give a range because I like to give extravagant problems. Let's say that there could be 8. There could be 1.
So,
There could be 10.
So for W2O2, would it just, wait, what is W, tungsten?
Tungsten.
Would it be tungsten to oxygen?
Tungsten to oxygen.
Oxide.
We'll see in a second. Andrew, you had a question?
Yeah, will you give us impossible compounds today?
No impossible compounds anymore. You're making me nervous. All right. Let's solve it. Okay. So let's see. Tungsten. There's 2 tungstens. Tungsten. That's what W stands for.
oh yeah.
Oxygen. How many electrons does oxygen need to have a full 8 valence
See, my
electrons?
question is, do you simplify it or do you not simplify it?
Oh, why not simplify it? You could if you want.
But it's fine if you don't, right?
Yeah, I just gave you this problem, yeah. It could be whoa, or it could be woo.
Okay.
What other one? So right here, how many does each tungsten have to give?
2.
2, yeah. So.
Wait, that crisscross applesauce works though.
Oh my god. So each of these tungstens, they give away 2. So we write it as tungsten.
You asked for the mark scheme?
2. And then what's the last part? Oxide, yeah.
Could you just give one more example?
Can you do it the other way around? Like,
Oh yeah, that's it.
You want me to give you the name,
Yeah.
and you want to figure out the formula. Okay. And then we're going to try 1 polyatomic ion, and then we're going to be just about done. Okay, Andrew, you got a question?
Even though it's W2O2 and it could be simplified or even like more complex,
Yeah.
does that mean that if you're given just one of those, you can put any symbol in the middle? Like,
Oh, I see.
W2O2, could you say
No, because even if this is W8O8, it's still going to be tungsten 2 oxide. Because each tungsten's giving away 2 electrons to oxygen.
Oh, right. Oh,
right.
So, but still you can write tungsten 1 oxide.
No, you can't write tungsten 1 oxide.
Didn't you told me that you can simplify it?
You can simplify this, the formula, but you can't simplify that. That's always going to be the same.
So, what's your...
So even if it's WO, it's still going to be tungsten 2 oxide.
So, for example, gold 6 oxide,
Gold 6 oxide.
you will not be...
Wait, let's stop right there. I want to do that. Let's do that. Gold 6 oxide, let's figure out the formula. Even though you have it probably written right there in front of you, I want to have everybody else look at this. Gold 6 oxide, what is the formula for that? What is the formula? I've given you the name. You tell me what the formula is. Can you do that? I know you can't.
Okay.
Someone's got their hiccups.
No, me too.
They're contagious. Lawrence had them earlier.
You need to isolate her.
So you don't simplify. Never simplify.
Wait, can I say that?
Let's try it out, yeah.
Never simplify, right?
Harris, Signe, if you guys aren't going to review. Oh, you're leaving anyway.
No, I'm not gonna get that.
Unnuggeting.
Yeah.
Awesome. Denuggifying. Let's...
Is it AU206?
AU... What?
That's what I thought, AU206.
AU206.
Does that work?
Yes.
AU206. So if you have gold, and you have oxygen, gold's giving away 1, 2, 3, 4, 5, 6. You're going to need to have... You're going to need to have how many golds?
6.
That's a lot. Wait.
You're going to need to have...
Wait, that doesn't work.
This is okay. You can have AU206, but a simpler way to do this is to say, okay, we've got to figure out how many oxygens are going to be around for 6.
Wait, wouldn't you give...
Is it AU3?
AU03, yeah.
Look, I'm just going to give this every single one of these oxygens first. Now these 2 are going to go right there.
Write that on the test.
These are going to go right there.
Yeah, because
That's just not the most reduced form. So you can have this, or you can have AU03.
But is it okay if I write it on the test?
Yeah.
gold only gives off 4 electrons, and you have 2 oxygens. Doesn't that mean that you can have AuO2?
If this gives off 4 electrons,
Yeah.
but this is giving off 6 right now.
Oh,
Right. Don't get tripped out by the Roman numerals. I give that to you guys as a gift on the formula sheet. I give you a list of Roman numerals. VI means 6. IV means... Harris? What does it mean?
IV 4.
Yes. It also
Wait,
means
you were
intravenous.
one other one. Because you drew out the second one.
I drew out this. I did not draw out this.
I'm like... Okay, so for the A206, I grabbed 6 oxygen.
Yep, that works.
They both, they all,
simplified it.
yeah, they, you simplified it.
From 2 6, I think of 2 6. But also equals 1 3. That's, I think of it as fractions.
But why, like, how do you, because you know how you say like transition metals like don't do it perfectly, like, they can give like however many.
Yep.
So then why is, wait, how many balance electrons are there?
AU is giving away 6.
Okay.
Oxygen just needs 2. So there's going to be, for every single gold, there's going to be 3 oxygens. Because each gold is giving up 6.
So wait, okay, gold is giving up 6, but you drew 6 oxygens.
You can if you like,
Right.
but because since gold is giving up 6, and each oxygen is taking in 2, okay, that might be the point where you're sticking. Each oxygen is taking in 2 electrons, right? So if each oxygen is taking in 2 electrons, and this gold is just giving up 6, okay, that means each one of these oxygens is going to take away 2 of the gold's electrons. So it takes away 2 there, it takes away 2 there, it takes away 2 there. So you're only going to need 3 oxygens to take up all of the gold's electrons. I think that you're kind of shutting down right now, because it's all out there. I'm gonna have you look at the tape again. Okay. Any other questions about this stuff? You guys look like you're all ready to get pumped up and get going.
Oh, wait, this is how we're doing this? Like, after this is like, is that
Yeah.
They said payback.
Let's cut the tape, and if you guys have any more questions, I can.
Can we just do a
Coming back in one.